We're going to look at the hypothesis testing process for variance and standard deviation in this section. If you recall from Chapter 7, we used Table G, or a chi-square score, to test for, or as a critical value for variance and standard deviation. So we are using a different table. If you also recall, that table had different columns at the top. So looking at that table, had different columns at the top. It had our 0.005, 0.01, and so forth. So there are different columns, and we'll use one or two of those columns depending on whether we have a right-tailed or two-tailed test, which is explained here in these three steps. If it's a right-tailed test, we simply use alpha at the top. And that should make sense because you look at your table, the right-hand side of the table contains the smaller numbers. Alpha is the area in the tail of the curve, so 0.005 or 0.01, 0.025. Those types of numbers are your alpha. They're on the right-hand side of the table. They're also used for a right-tailed test. If our test is left-tailed, we use 1 minus alpha. So again, 1 minus this gives us 0.995 or 0.99, 0.975. Those types of numbers are on the left-hand side of the table. It's a left-tailed test, so we'll look up on that side. If it's two-tailed, we're going to use two columns, alpha divided by 2 and 1 minus alpha divided by 2. So keeping in mind that those numbers are used along with our degrees of freedom. Degrees of freedom are our sample size minus 1. We'll use those alpha numbers along with our degrees of freedom to find the critical values that will go on our curve based on a right, a left, or a two-tailed test from the table. And then down here we have our test score formula. A chi-square score is our sample size n minus 1 multiplied by our sample variance. Hopefully we're accustomed to these symbols by now. S squared is our sample variance, and sigma squared is our population variance. It is an important side note that these values are variance numbers. Our calculation compared to our chi-square scores are based on variance, so these numbers have to be variance regardless of whether we're testing for standard deviation and or variance. So from here, we'll go ahead and move on and try our first example. You can read here, manufacturer wants to know if the variance, the size, the diameter of a nut, so we're testing variance here, is equal to 12. A sample of 17 had a variance of 10.6. Test of the variance is 12 at the 0.01 level. So in step number 1, we'll write our two hypotheses based on a variance. Quick little cosmetic change there. In the past sections we've worked with mean, we've worked with proportion. They had different symbols, the mu and the p. We obviously have a variance here, so that is our sigma. And that's based on a variance of 12. And over here, our alternative hypothesis, also based on a variance of 12, wants to know if it's equal to 12, so equal to and not equal to, and this then would be our claim. Quick reminder that our null hypothesis always contains our equal to sign. So you'll note here that we have a two-tailed test, which means we use alpha divided by 2 for a column, and we use 1 minus alpha divided by 2 for a column. Alpha is 0.01 from here. So we divide that by 2. One of our columns that we'll use to find our critical value is 0.005, and one of our columns is 1 minus 0.005 or 0.995. So I'm going to sketch my curve over here, making a note about our curve. Previously, we worked with a normal distribution curve. We had 0 down the middle, and we had negative values on this side and positive values on this side. Well, with our chi-square, we don't have a 0 down the middle. We start at 0 on this side and work our way up, so all of our values are positive. In other words, one more time, if we start at 0 right here and work our way up, there are no negative values for our chi-square distribution. They're all positive, starting at 0 and working our way up. So we have these two columns. I'll also mark on here our degrees of freedom. Our sample size is 17. Which means we have 16 degrees of freedom. So I'm going to go to our chi-square table. We have 16 degrees of freedom, which would be down here. And if we went across to 0.005, we find 34.267, and back over here 5.142. Those are our two critical values. 34.267 is our right-hand side, and 5.142 is our left-hand side. If you ever have any issues on which one goes where, again, we start at 0 and work our way up. So the larger number goes on this side, the smaller number goes on this side. And then we also have a right versus a left-tailed test. In this case, we have a two-tailed test. Step number 3, we have a new formula for our test score. Our chi-square score is our sample size minus 1, so 17 minus 1, multiplied by our sample variance. Our sample variance is 10.6. Divided by our population variance is 12. So notice I'm not squaring those values because they're already given as the variance. S squared was a symbol for variance. Sigma squared was a symbol for population variance. I don't need to square those values. I just put those in there and make my calculation. So I get a test score of 14.13 when I calculate that. 14.13 is going to fall between 34.267 and 5.142. In the unshaded area means we do not reject the null. And in this case, since the null is true, that means the claim is also true. So there is enough evidence to support the claim. Okay, so we talked about this before. We have the same 5-step process all the way through. We saw a bit of a change here in steps 2 and 3 with our different table to use. We're using table G based on a chi-square distribution, the fact that we're testing variance and or standard deviation, and we have a different chi-square for our test score formula here to come up with that test value. A couple more times here. Teacher claims a variance on a certain test is less than 68. Sample of 58 has standard deviation of 5.8. Test the teacher's claim at the 0.01 level. Notice we're testing variance again, so there's our symbol for variance, sigma squared. Based on a variance of 68, our teacher says it's less than 68, so this is less than, which means this is greater than, and over here is our claim. We have a left-tailed test. For a left-tailed test, you recall we use 1 minus alpha, which in this case is 1 minus 0.01 or 0.99. Our degrees of freedom is 57. We have a sample size of 58, so we have 57 degrees of freedom. We have a left-tailed test, so I'm going to shade on this side right here. Then I'm going to go to the table and use the column of 0.99, which is on the left-hand side of the table, along with my degrees of freedom. So taking a quick peek at that, we have a unique situation that pops up here. First of all, our 0.99 column is right here. As I scroll down, I don't want to go too far. Notice we go from 50 to 60. We don't have a 57 in there. So our book wants us to be conservative, so never going over our sample size. So we're going to go down to 50. That test score, our critical value is 29.707. So I'll plug that into our diagram here. 29.707 is our critical value. We'll move on and calculate our test value. Our sample size is 58 minus 1 multiplied by our sample variance. I need to backtrack on that. My sample standard deviation is 5.8. So notice it's standard deviation. I do have to square it this time because 5.8 squared would give me my variance. 68 is already a variance number, so I do not have to square it. Just reiterating our relationship between standard deviation and variance from Chapter 3. The standard deviation is the square, or the square root of the variance, or the variance is the square of the standard deviation. And if we calculate that, I get a test score of 28.20. Keeping in mind our scores all go from 0 on up, so 28.20 is going to be to the left of 29.707, which tells me this time to reject the null hypothesis. And since we reject the null, this is false, which means our alternative is true. Our claim is also true, so there is enough evidence to support the claim. All right, so noting we had the standard deviation given to us, we did have to square that to make it the variance. So just pay attention to those details there. Okay, we got one more to go through here. Hospital administrator believes standard deviation of the number of people using outpatient surgery is greater than 8. Random sample of 15 days is selected. Standard deviation of the sample is 11.2. At the 0.01 level, is there enough evidence to support the administrator's claim? Assume the normal distribution. So we're testing the standard deviation. Notice a slight symbol change here in step number 1 is greater than 8. So our two hypotheses based on a standard deviation being greater than 8, greater than or less than, our claim would be our alternative. Notice I don't have a sigma squared here, I just have sigma because I'm testing the standard deviation, not the variance. We have a right-tailed test this time. Right-tailed uses simply alpha, so alpha is 0.01 along with our degrees of freedom. Our degrees of freedom, we have a sample size of 15, so we have 14 degrees of freedom. We'll take a quick look here. 14 degrees of freedom along with 0.01 gets us down here to 29.141. So that's our critical value. I'll plug that into my curve here. It's a right-tailed test. So 29.141 goes here. We'll shade to the right on a right-tailed test. We'll move down and calculate our test score. Our sample size is 15 minus 1 times our sample variance. Our standard deviation of the sample is 11.2, so our variance is 11.2 squared. Our population standard deviation is 8, so we have 8 squared down here. And that gets me a test score of 27.44. 27.44, moving from left to right, will be to the left of 29.141, which tells me to go ahead and not reject the null. Do not reject the null. And since we did not reject the null, we're saying the null is true. We're saying this then is false, which means the claim then is also false. So there is not enough evidence to support the claim. And there's a quick look at our testing process, hypothesis testing for variance and standard deviation.